In this statistics video, we are going to talk about the normal distribution. So if we have a continuous random variable that has a distribution with a graph that can be described by this equation. So this one's kind of fun looking, right? We've got 1 over sigma square root 2 pi times e to the negative 1/2 times x minus the mean over sigma, standard deviation, quantity squared. What's going to happen if we graph that is that we're going to create this bell-shaped curve. So I've done that in Desmos. So over here at Desmos, I'm using S for the standard deviation instead of sigma, and I'm using M for the mean instead of the mu Greek letter that you see in the formula. And you can see that if my mean is 0 and my standard deviation is 1, it's going to create this really nice, beautiful, symmetric distribution here. And that's really what we're focused on. Now, notice that if my mean changes, I'm still going to be normally distributed. It's really just shifting everything left and right. And if I were to change my standard deviation, let's go back to 0 here. If I change my standard deviation, notice it changes that spread. I'm going to zoom a little bit so we can see that better. So if my standard deviation is 1, it looks like that. If it goes bigger, notice this thing starts to flatten out. And if it gets smaller, it gets really skinny. So it's affecting that horizontal compression there, whereas the mean just shifts it left and right. So, but the one we're talking about here, you set this back on 0, where the mean is 0 and standard deviation is 1. This is called your standard normal distribution. Mean is 0, standard deviation is equal to 1. And what we used to do is we used to take problems that had different means and different standard deviations. Maybe we're talking about IQ scores that are normally distributed with a mean of 100 and a standard deviation of 15. And we could kind of put them on the same scale and we could standardize them. And the way we did that is we used that z-score formula going way back to, I think it was around chapter 3. So we took all of these values and we standardized them using a z-score, and then now we're going to figure out what the probability is under the curve. So if I'm looking at a z-score of less than -1, I'm looking at this area under the curve here from negative infinity, okay, because even though it's getting really close to the axis, it's actually not touching the axis. So there's a teeny tiny bit of area there, all the way up to our value of -1. And remember, we said it doesn't matter if we do less than or equal to, or we do just less than, we're going to get the same answer either way, because we're talking about that area under the curve, and that area at -1 would be very, very, very tiny, very minuscule there. So that's where we're heading. Let's go back to our notes. But before we jump into that, let's look at some properties of the standard normal distribution. So that first property is really talking about the mean and the standard deviation. So the mean is 0 and the standard deviation is going to be normal. And we can standardize everything using that z-score formula. Second property is really similar to the uniform distribution in that that total area under the curve has to be equal to 1. And we could prove that if we wanted to. That gets into some calculus things. Be a fun thing to ask a calculus teacher later on. And then another property is that we have a bell-shaped distribution. And it's going to be symmetric about the mean. So let's look at some notation here. It's going to be really similar to what we saw before. If I'm looking at the probability that Z is between A and B, we could write it that way. That Z is referring to the Z-score. I want to find the probability Z is greater than A. I'm finding the probability that the Z-score is bigger than some number. So graphically, what's going to happen? Let's say our value, let me put A here. If I'm looking at the probability Z is greater than A, I'm looking at this area. Whereas here, if I'm looking at the probability I'm between A and B, I'm looking at this area in here. And these areas are not as nice as the uniform distribution. They're not rectangles. They're not as easy to find. So how do we find that area for that shape that's not a nice shape? That's where we would use technology to do that. Back in the day, we had z-score tables that we would use. Now we can use technology and be even more accurate than what we were with those tables. And then the last one, probability Z is less than B. So here's B. Less than would be over here. And where's that? Or less than B would be on the left-hand side. For a normal distribution, a critical value is a z-score on the borderline, separating the z-scores that are likely to happen from those that are unlikely to happen. And we're going to see critical values come back up when we start talking about confidence intervals and hypothesis testing. So just to give you an idea of what that's going to look like and some notation associated with that. So this would be the area to the right. So my critical value, I could write that as Z sub alpha. So for instance, suppose that area in that right-hand side was 0.05. Then if I wanted that critical value, I would write it this way, Z of 0.05. That's a subscript on the Z. And we would want to find that z-score that's associated with that. We would do that using the standard normal distribution. That's the one where the mean is 0 and the standard deviation is 1. And that's going to find a critical value. And that will be important when we start doing hypothesis testing and stuff. And I'll show you how to use technology to do all this. So let's look at a few examples. So in these pictures, we want to find the area of the shaded region, and they're giving us a z-score. So that first one is asking us to find the probability that z is less than 0.44. Okay, less than because we're shaded to the left of 0.44 as our z-score. So I'm going to go to my SALT technology, distribution calculators, and this is the normal distribution with the standard mean and standard deviation. So 0 and 1. I want to find the probability that I am less than. So I'm looking in that left tail. Notice what's shaded down here. picture there. So less than 0.44. When I type that in, I'm going to get my z-score value, my area value, 0.6700. And I'm going to round these to 4 decimal places. That's typically what's standard. If I look at number 10, I'm trying to find the probability to the right of this z-score. So z is going to be greater than negative 1.04. And again, I'm going back to my SALT, which is my Cengage learning tool. This time I want to know what's going on that right side, so the right tail. Type in negative 1.04. Here's my probability, 0.8508. And then let's do one of these. Number 11, I'm finding the probability that I am between negative 0.84 and 1.28. So I'm going to use between. Notice it's shading between two z-score values. So I want to be greater than negative 0.84, but I want to be less than 1.28. I get 0.6993 if I go 4 decimal places there. So let's look at a few more examples. Notice in these, they're giving us an area. They're asking us to find the z-score. So we're trying to find the probability. On this side, I'm shaded to the left, which means less than. I'm looking for some number. That's what I'm trying to find. And that probability is 0.8907. So we can use our technology to figure that out. Mean is 0, standard deviation is 1. This is still a standard normal distribution. And I have area in the left tail. And this time I'm going to type the area in here, and it's going to pop up that z-score value here. So I'm going to type in 0.8907. And when I do that, I get a z-score of 1.23. And I am going to round the z-scores to 2 decimal places. So my value here is going to be 1.23. If I were to look at this one, notice it's shaded to the right. So I'm looking at greater than here. I'll call this B. It doesn't really matter what we call it. And we know that area is 0.9265. So we are looking for that z-score. So going back to our technology, we are now choosing the area to be in the right tail. And we're typing in 0.9265. And then we're going to get that z-score out of negative 1.45. And we can look at either place here. So that's equal to negative 1.45. So that's using the technology to find a z-score if we have an area, like we did here, or finding the area if we had a z-score or 2 z-scores. Now, what if we don't have a picture? Well, in that case, maybe we need to draw a picture. We can still find areas associated with values. Let's look at a few of these. Let's look at number 20. They're asking us to find the probability that we have a z-score of less than 2.33. Notice this is still a standard normal distribution. So trying to find the probability that z is less than 2.33. So if we were to draw a picture of that, 0 is in the middle. Here's 2.33. It's going to be shaded to the left of 2.33. Technology, left tail. Z-score is 2.33. Our probability is 0.9901. Let's say we want to find the probability. We're between 1.5 and 2.0. So if I were to write that as a sentence, it would look like this. 1.5 or 1.50 is less than Z is less than 2. Picture. Zero's in the middle. Here's 1.5. Here's 2. And these pictures do not have to be drawn to scale. Just want an idea of what it's going to be. That's going to be a small area, right? It's definitely going to be less than half. Technology, between, mean, standard deviation is at 0 and 1 respectively. Between 1.5 and 2.0. And my area is 0.0441. And then let's look at one more. Suppose we want to find the probability that we are greater than negative 3.77. We would write it as Z is greater than negative 3.77. If we wanted to draw a picture, here's 0, here's negative 3.77. And this is going to be a big chunk of our graph, right? It's going to be really close to 100% there. So we're going to technology. We want the right tail. Our Z-score is negative 3.77. You can see we're going to get 0.9999. And then now we need to talk about those critical values. And this is going to work the same way as the other problems that we did. That's going to help if you draw a picture of what's going on. So let's look at 41. We want to find the critical value associated with Z of 0.25. So if you remember, critical value is giving you the area in that right tail. So this area is 0.25. Okay, so I'm shading that to the right. So I want that right tail checked. And my area is 0.25. My Z-score, rounded to 2 decimal places, would be 0.67. So that would be the critical value. That's the critical value that separates that top 25% from the rest of that graph, that lower 75%. Let's do another one. Let's look at this one. Z of 0.05. So we're going to draw a picture. We want that 0.05 as the area in that right tail. We're going to use the right tail, type in 0.05, and we're going to get 1.64. And this is a critical value that happens quite a bit. This is the only one I've ever seen that tends to get rounded to 3 decimal places. And that's just because it comes up a lot. There's a lot of times you want to be 95% confident, which would leave 5% in the tail. And we'll talk more about that when we talk about confidence intervals and stuff. So I am going to round that one to 3 decimal places, 1.645.